Having now recognized that a simplistic notion of control is not going to be adequate to the task of describing the role of the brain or the nervous system in bodily movement, and that our attention should be rather on modes of coordination in which the diverse and complex elements of the body come together and work in harmony towards goals. We need to develop a vocabulary for talking about this. Movement science has developed its own vocabulary here, and the terms are not those terms that you will get in behavioral science, because they won't speak of minds. The behaviors in question will be the kind of behaviors that we observe in many kinds of animals. So our commonalities with fishes, bats, and jellyfish are at stake here. So we need some very basic, secure concepts with which we can approach the body as it moves. Now, one of the most obvious characteristics of animal movement is that bodies propel themselves by pulsing, oscillating, flapping, wagging, all different kinds of what we might call oscillation. That is a physical movement which repeats in a cycle. That's true for the jellyfish and the bat and you. Because we're adopting a physiological stance, we need to be considering the physics of the body. And bodies have certain properties. Different bodies will have different properties, but they will all be massive. The size of the various parts is going to matter. When we approach locomotion as the most fundamental of behaviors, as it were, then we can ask about the physics of locomotion. Most behaviors won't allow that kind of preciseness and robustness. So we're dealing here with the organism considered as an embodied being, and the embodiment is absolutely central. Despite the wide variety in body parts, this single notion of oscillation is going to guide us as we look at how different body parts become non-independent as they move in a coordinated fashion in order to move the animal around. So we need a technical language for this, and it turns out, of course, that we have very, very strong and robust mathematical concepts to help us out here. So we need a basic mathematical figure to bring to bear as we begin to describe the wide variety of forms of coordination found. And because we're dealing with things that repeat, the cycle is going to be of fundamental importance here. When something repeats periodically, goes up and down or back and forth, we can describe it as an oscillator. Now, that's a mathematical abstraction because, of course, mathematics abstracts away and tries to find those forms that will make the messiness of the real world intelligible. When something goes through a cycle, we will often need to say where it is in that cycle. The technical word for this is a heavily overloaded word. It's used in various ways, but here when we're describing where we are in a cycle, we will describe that as phase. The phase of an oscillator is where it is in its cycle. And because these concepts are so fundamental and used by a wide variety of communities, engineers, mathematicians, theoretical physicists, we find different conventions here, but they're all expressing the same basic idea. We need to be able to describe using a number where a repeating system is in its cycle. I've shown three conventions for noting phase there. On the left, you can see if we start at 3 o'clock at the right-hand side, call that 0, and we'll go anti-clockwise around this circle. And then we can see we go a quarter way through, a half a way through, 3/4 a way through. And when we end up back at 1, then that's the same point at which we started at 0. So that is a phase convention that notes the place within a cycle with a number between 0 and 1. That's my favorite convention. The other ones are just a little bit more obscure because they use notions from trigonometry. So a circle can be described as 2 pi times the radius of the circle. And so these conventions come from those for whom that kind of thinking is very natural, and so we can describe the same thing as being either from minus pi to pi or from 0 to 2 pi. And both of these rather more obscure conventions coexist with the simpler idea of simply noting between 0 and 1. The core idea is phase just tells us where we are in a cycle. And now we will have to address a situation in which we have more than one oscillator. When we have two or more periodic things and they can influence each other, then that has consequences. They will influence each other and become somehow non-independent, become entrained or couples. Those are technical terms that describe this non-independence. If you have two pendula, for example, just simple pendula, and they're hanging from a common string, then the movements of one will interact in really complicated ways with the movement of another. I'd like to demonstrate the notion of entrainment here using metronomes. There are 5 metronomes here. Each of those can be considered as a separate oscillator, and initially they don't influence each other. And now I'll just let the video maybe speak for itself. Remarkable, huh? So you heard various things there. You heard those metronomes initially assert 5 different rhythms, as it were. And then when they were placed on the cans, they could influence each other through the small vibrations that passed through that plank. And you heard them get into lockstep, as it were, into synchrony. But you heard something else, because they didn't just get into lockstep. When they were on the plank, you heard them move in and out of patterns of mutual coordination. Because each of the independent metronomes has an endogenous rhythm, one that comes from within, and that is in a state of tension with the influences from other neighboring oscillators. The mathematics of the means by which oscillators influence each other is very well developed and has been used in all the physical and biological sciences and beyond. And it's entirely generic. This is a way of understanding how the world works. Those metronomes don't have brains. Those metronomes don't have control systems. But the kind of phenomena that we see there operating between the metronomes will apply when brains and bodies are involved as well. The dynamics of entrainment are entirely generic, and they provide a very useful way of capturing both the relationship between the autonomy of the individual, because each metronome asserted itself, and the collective pattern that arises through their interaction. And this is useful for us because when we survey a wide variety of body types, we find that there are some basic, simple principles that underlie the coordination of the various body parts in all animals. Not all animals have limbs. We're most familiar with locomotion that involves limbs, 2 legs, 4 legs, 8 legs, always an even number of legs. And limbed coordination allows for a particularly simple form of description where we can look at where one limb is with respect to another limb. That is, describe the relative phase of limbs, paired limbs. So out of this, one very influential model, which we won't go into in detail, but it will inform a lot of what we see in the next few videos, comes from an Irishman, Scott Kelso from Derry, in collaboration with Hermann Haken, a physicist from Stuttgart, and The third author is Bunce. I know less about him. But this is an old model that goes back to 1985, and it founded a whole field known as coordination dynamics. So dynamics refers to patterns of change, and coordination to the arising of non-independence among the parts. And at the heart of this, the original implementation, as it were, was a model system which was very, very simple. You could dream it up sitting on a bar stool. This model system considers two wagging things, two limbs, two flippers, two wings. In this case, because we're sitting on a bar stool, we'll use just wave two hands or wag two fingers. If you are given the task of wagging two limbs or two fingers at identical frequency, how many patterns do you think you can give rise to? Well, you can try it out for yourself, and what you'll find, doesn't take long, is that this pattern is fairly easy, where we wag. We'll call this the in-phase pattern because, let me stop that, each digit here, or hand in front of my face, is going through its cycle at the same time. They're starting in the same position, and they always are the same position within their cycles. So each hand is at the same phase of its cycle at all times. We'll call that the in-phase pattern. And there's another pattern you can do. Here, each finger or hand is a half a cycle out of step with the other. This is like a syncopated pattern, if you like ska music, and we'll call it the anti-phase pattern. Now, curiously, those are the only two patterns that exist. You can try to maintain any other stable phase relationship between the limbs, but as long as you adhere to the task requirements of wagging them at an identical frequency, those are the only two coordinative modes that you can find. Furthermore, there are some interesting properties, and the exact nature of the more detailed properties that we observe in a given system are going to depend on whether we're talking about wings or legs. Obviously, this matters. And in this case, we're talking about hands. So it has some peculiar properties, but they're of a kind with the kind of properties we observe in groups of legs. So one thing that's interesting about this system is if you start off in the antiphase pattern and we speed up, so we increase the frequency at which you're to wag the hands, then after a certain stage, when you get fast enough, the antiphase pattern becomes unstable and will readily flip into the in-phase pattern. So you'll start off doing this and you'll end up flapping. Now you can resist this and then the whole thing becomes unsteady, but you can feel this in your hands as you speed up from an antiphase pattern. It's just much easier to fall into the in-phase pattern. And this should remind you of something. It should remind you of what happens when you speed up a walk. And there comes a point at which, based on rate, you have to reorganize your body and find a different way of coordinating your legs as you switch into a run. So this kind of thing arises again and again in slightly different form each time with different bodily structures. So this system has a lot of interesting properties that have merited a ton of study and modeling. There are two stable modes at moderate speed, the in-phase and the anti-phase pattern. There's a rate-dependent transition to one of those two modes. That happens if you go faster. There's no comparable transition as you go slower, and that's different from running and walking, for example, where if you walk faster and faster, you'll switch to a run. But if you run slower and slower, you will switch back to a walk. So that's a slight difference here. And when you study the detail of this, as the coordinating elements approach the point at which they switch from one mode to the other mode, we find a great deal of variability. They become somewhat non-independent just prior to the switch, a phenomenon known as critical fluctuations, empirically observable in many kinds of systems, and very useful for telling us that this system is about to undergo a switch from one global form of coordination to another. So those are some basic mathematical principles with which we're going to approach movement and coordination as we go along.